Hi, Professor Ho and Professor Choi. Today I would like to present my final year project on the effectiveness of diabetic shoes in ulceration prevention. My presentation will be divided into 6 parts. First, the inspiration and objectives of this project. Second, the introduction on epidemiology and etiology of diabetic foot ulcers. Third, the insole prototype design, including material selection and fabrication procedure. Fourth, the method, including material-based experiment protocol and data measurement. Fifth, further experiment on thickness-based insole testing. And finally, the discussion. So without further ado, let's start the presentation. This topic is a self-defined study. It was inspired by the previous research I have participated in the BME Overseas Summer Research Internship. Study of the effectiveness of local vibration on microcirculation improvement in diabetic patients not only broadened my horizon, but also helped me to gain my interest on the disease of diabetes mellitus, which led me to choosing this related topic. There are 3 major objectives in this study. First, to review the epidemiology, etiology, and management of diabetic foot ulceration. Second, design a simple flat insole prototype. Third, compare the effectiveness of insole in different materials and different thicknesses. Diabetic foot ulcers are one of the major complications of diabetes mellitus. It was defined as a full-thickness lesion of the skin distal to the malleoli in a person with diabetes mellitus. In UK, 7.4% of diabetic patients had a history of active or previous foot ulcer. Moreover, even when an ulcer is successfully healed, the rate of ulcer recurrence is immense, between 30 to 40% within the first year. In addition, every 30 seconds, a lower limb is lost to diabetic foot somewhere in the world, which leads to the enormous economic burden personally and socially. Personally, patients with lower extremity amputation generally need to spend between $30,000 and $60,000 yearly and $500,000 in their lifetime. Socially, in 2012, between 639 and 662 million pounds were estimated to be spent on foot ulcers and amputation treatment from the UK National Health Service. Before we get into the causes of foot ulcer, let's talk a little bit about the anatomy of foot and ankle. The anatomy of foot and ankle consists of 26 bones, 33 joints, with muscles, tendons, and ligaments to provide the body with supports, balance, and mobility. Also, the unique structure of the foot arch acts like a spring, which distributes the body weight in different regions on plantar foot like hallux, metatarsal heads, heel, etc. So let's move on to the etiology. Diabetic foot ulcer have a multifactorial etiology. Neuropathy, ischemia, and deformity are the 3 major causes. Neuropathy has both in autonomic and somatic way. Autonomic neuropathy leads to the dysfunction of the microcirculation with reduced distribution of blood to areas needed. On the other hand, both sensory and motor nerve could be damaged in somatic neuropathy. Damaged sensory nerves result in the lack of awareness of ulceration, and the damaged motor nerve affects the muscle for foot movement, abnormally redistributing the forces during walking. So let's get into the research part. The research workflow is shown as chart below. The criteria for choosing the material are based on the ability to relieve pressure, attenuate shock, the popularity, and the availability. First, the ability of pressure relief is determined by the stiffness of the material. Lower stiffness has a better mobility to increase the surface area contact to the foot contour. According to the equation of pressure equal to force divided by area, this results in a reduction of peak pressure. However, stiff material is good at providing support, control, and stability, which is also a necessary property for insole. Second, the ability of shock attenuation is determined by both density and resilience. Lower the density, better the shock absorption. However, material with too little density may lead to the bottoming out effect, which eventually lead to poor ability to attenuate shock. The lower the resilience, the greater the damping or shock attenuation capacity. It can be calculated as resilience equal to rebound height divided by drop height experimentally. Based on the criteria just mentioned, the theoretic performance of 4 commonly used insole material were compared. 3 stars represent the maximum performance, accompanying 1 star as the minimum performance. According to the table, cork and poron were expected to have the best performance. EVA has a fine performance, while plastosols has the worst. Although porons has a great performance, it is not available on the Taobao. Therefore, cork and EVA were selected to be investigated. To create an insole, step 1, a pair of commercial insole was used for tracing the insole shape on the material sheet. Step 2, cut the insoles by scissors for both left and right foot. Step 3, repeat step 2 to make 2 layers of 3 mm insoles for each foot. Step 4, rub the edge by using 2 different grid destination, P100 and P120. From less dense to denser destination. Finally, stack 2 layers of sheet into double layer insole prototype. Now, let's talk about the experiment section. The experiment protocol will be conducted at the Creative Design and Invention Center of Asia University in Taiwan. I will be supervised by and alongside with Professor Chi during the period of visit from 18 to 24th of December. 5 healthy subjects without any foot abnormalities will be participated in this study. They will be asked to perform a 10-meter walking task. Pressure, insole temperature, and humidity will be recorded during the task. Before the task begins, subject will be asked to do a 3-minute walk to reduce temperature effects. Also, subject will be instructed to walk at the normal pace in order to reduce the walking speed effect. Moreover, the measurement will only be taken from the 3rd, 4th, and 5th step to avoid confounding effects of acceleration and deceleration. 10 anatomical regions method will be used to separate the measurement in different parts. With the figures shown on the right side, different labels represent different divisions of pentafood. Equipment F-scan will be used to measure peak pressure and force time integral. Peak pressure is defined as the maximum pressure recorded by any sensor within a region. It can be denoted by equation of pressure equal to force divided by area. Force time integral is defined as the total sum of pressure multiplied by the area of sensor and contact of all sensor encapsulated by the anatomical regions. It can be denoted as below. There are few research study the in-shoe environment condition like in-shoe humidity and temperature. Since it is believed that the cause of skin breakdown can be a combination of pressure and also the temperature and humidity within the shoe. Also, the increase in humidity and temperature may affect bacteria on feet. In addition, the change in temperature can be evaluated as the ability of material to evacuate heat from the plantar foot. Therefore, temperature and humidity should be included in this study. Equipment Adreno with SHT cross VO2 multi-sensor. A combination of temperature and humidity sensor was used. It will be put in the region of 2nd to 4th toe of the midsole of the sample diabetic shoes. A part of the midsole has to be cut for fitting with the sensor. The adrenal coke is shown as below. Apart from the scientific data, the perception from subject is also an important parameter to evaluate the compatibility of insole subjectively. This parameter has never been used for any studies on diabetic shoes. Visual analog scale from 1 to 10 is then introduced. The score of 10 represents the maximum comfort, accompanying 1 as the minimum comfort. It will be asked after the 10 meters task. The thickness-based experiment is proposed for further experiment. After the best material is concluded, different thickness of 6, 9, 12, 15 mm will be investigated. Thickness thinner than 6 mm is excluded because it may have poor shock attenuation property. The thickness thicker than 15 mm is excluded due to its incompatibility with the diabetic shoes. When the thickness is increased, the pressure is expected to decrease with increased in-shoe temperature and humidity, and the scale of comfort is expected to decrease. Throughout the fabrication, flaws were made from the handmade of insole prototype. The uneven surfaces on the edge of insole, it can be solved by using sandpapers. Also, there might be deformation in the material. Avoid applying excessive force can reduce the effect of compression deformation. However, the fabrication can be improved by using manufacturing cutter like laser cutters, creating edge with high quality finish. This is the end of my presentation. Thank you so much for listening.